Okay, the first section that we're going to talk about has to do with when you have two events that happen at the same time. Everything that we've talked about so far has been like the probability of one thing occurring. Well, in life, one thing doesn't occur very often. Most of the time, it's a couple things that occur at the same time. And so when you have two things that you're trying to get to occur at the same time, you multiply their probability together. Like, for instance, all right, there is, if you open your book, on page 739, there's a transportation information there. It says, on 739 at the top, it says, one study found that when an airplane is more than 80% full, there's a greater chance that the flight will not depart on schedule because of the time it takes to stow all the carry-on bags. As a result, the flight may not arrive on schedule. A travel agent informs a customer making flight reservations that the probability of her flight to Nashville will arrive on schedule is 85%. Her flight to Denver is on a different airline and has an 80% chance of arriving on schedule. What is the probability that both of her flights will arrive on schedule? Now, two different events. Does the one plane have anything to do with the other plane? No, but we want to know, and the key to this particular section is the word and. Okay? The question said, what is the probability of that both of her flights, so this flight and this flight, will arrive on schedule? So the probability of the first flight is 85%. Okay. Any idea what the fraction value of 85% is? How would I find it? 85% is the same as 85 over 100. Okay, so if I want to reduce that down to lowest terms, I've got 85, oops, as I write 84, 85 divided by 100, and I'm going to convert it back. It's going to give me a 17 over 20. Okay, that's the probability of the first flight. The second flight has an 80%. So again, that is 80 over 100. If I make it into a decimal, it's obviously 0.8. Go backwards, it's 4/5. Okay, so far so good. All I did was, this is the probability that the first flight will arrive on time. This is the probability that the second flight will arrive on time. Okay, they are independent of each other. The first flight arriving on time doesn't have anything to do with the second flight arriving on time. Okay, it's not like one is dependent on the other. So the probability of, if you say A and B, will be 17 over 20 times 4 over 5. So I multiply this out, it's going to give me a 68 over 100, which I'm going to reduce down, and then I'm going to convert it back to a fraction, and it's going to give me 17 over 25. That is the probability that both flights will arrive on time. Does that make sense? I mean, it's doing the exact same thing that you did in the last section, but this is more than one event. Okay? Let's do another one here. Every Friday, the physical education class goes bowling at the local bowling alley. On one shelf at the bowling alley, there are 5 black and 3 green bowling balls. Let's write down that information. Okay. One student selects a bowling ball at random from the shelf and puts it back because it's too heavy. The second student then selects a ball from the same shelf. What is the probability that each student picked a green ball? Okay, so how many total are there? There's 8. So let's talk about the probability of the first student picking a green ball. Okay, how many possibilities are there? There's 8. How am I going to know the total number of possibilities on the bottom? What is that going to be?
3.
Okay, well, it's the combination of 8 things, or 3 things, taken one at a time, because they're only selecting one bowling ball, okay? But actually the bottom would be 8 things taken one at a time. Those are the number of different ways they can be selected. The top would be the combination of 3 things taken one at a time, correct? That's for student 1. Student 1 puts the ball back. So the second student has the exact same probability of selecting a green ball. So it's the combination of 8 things taken one at a time underneath the combination of 3 things taken one at a time, right? Because one event does not affect the other one. Now, if that person had not put it back, that would be different. We're going to talk about that in a minute. But did you figure this out? Okay. What is the combination of 3 things taken one at a time? 3. 3. What is the combination of 8 things taken one at a time? 8. 8. Okay. So therefore, this is what we have, right? So we have 9 over 64. That is the probability that both of those students will select a green bowling ball. Okay? Now, let's change this up for a minute. Let's say student 1 selects the green bowling ball and decides to keep it. Okay, it's not too heavy, they're not going to put it back. How does that change this?
2.
Okay, it not only changes this to 2 on the top,
7 on the bottom.
but it changes it to 7 on the bottom because I've now taken one bowling ball away. Okay, so then this becomes 6 over 56, or if I divide both of them by 2, it's 3 over 28. Okay, does that make sense? So you have to pay close attention to what they're saying about the event. Logically, think about the fact that if you select the bowling ball is not there for the next person to select, okay? But if you put the bowling ball back, then everything is going to stay the same between the first person and the second person. Yes, no, maybe? Okay? All right, I'm going to put something up here, and I'm going to ask you a question on it. Pretend those are all equal, okay? Y'all know me and my drawing skills. Or lack of. Alright, so this is like a spinner, if you will, okay? Suppose you spin the spinner below twice. We're going to do it 2 times. Find the probability of a B and then a C. Okay, go ahead and figure it out for me. Okay, what's the probability of getting a B when you spin it the first time and a C when you get it the second time? should have 1 over 18. So Chad, 1 over 18? Yes? No. Okay, the probability of getting a B, okay? There's 6 spots, okay? So basically I can say this is 2, 6, okay? The probability of getting a B is 2 out of 6 or 1/3. Probability of getting a C is 1 out of 6. So all I have to do is multiply the 1/3 times the 1/6, which is 1/18. These are independent events. Getting the B the first time I spin it has absolutely nothing to do with whether I get a C the second time I spin it. Okay, they are completely independent of each other. Does that make sense, how they don't affect each other? Okay, all right, here's another one. All right, you got a bag that contains 6 orange, 8 blue, 4 yellow marbles. Okay, those are marbles. Okay, what is the probability of selecting 2 marbles? 2 blue. Okay, I want 2 blue, the probability of 2 blue marbles. Okay? If it's drawn first and then replaced before the second one's drawn. Okay, so you're going to draw a marble, then you're going to put it back in the bag, and then you're going to draw another marble. So what is the probability that you draw a blue marble, and then you turn around and you draw a blue marble the second time? Now you could do this with combinations, but you don't have to. I mean, you can do it just going, okay, how many choices are there and how many of those choices would be successful. It works with combinations, but you certainly don't have to do it that way. Should have 16 over 81. No. Okay. How many different marbles are there? 18. Okay, so I have 18 on the bottom because that's the number of choices I have. The number of successful choices would be 8. Okay, now if I want to reduce that down, I can divide both of them by 2, so I have 4 over 9, right? Now, if I'm going to put that marble back, then the second time I do this, it's going to have the same probability. So I'm going to go 4 times 4, which is 16, 9 times 9, which is 81. Okay? Now, the next, let's say I do this again, but this time I don't put the marble back. Okay? Then, this what I just did is considered independent. But if I don't put the marble back, it's dependent because the one choice affects the second choice. So the first time I would have an 8 over 18. How does that change for the second choice if I don't put the marble back?
7 over 17.
7 over 17. Okay, because I've taken one of those blue out of the mix. So now I only have 17 blue, or 7 blue, and I only have 17 marbles. Okay, so the probability, if I don't put it back, would be a 56 over, let's see, 18 times 17. 306, but I can reduce that down. And it reduces down to 28 over 153. and that would be the probability if I don't put the marble back. Does that make sense? Okay, what if I, still asking the same questions here, what if I said, you know, I'm going to, I want to know the probability of getting an orange and then a yellow, and I'm not going to put it back, okay? I'm going to draw, I'm going to pull out an orange, but I'm going to keep the orange. I'm not going to put it back. Give me the probability of getting an orange and a yellow. Makes sense. What would have changed if I put the marble back?
17.
This is the only thing that would have changed right here, is that 17 would have become an 18. Make sense? Logically? Okay, all right, let's do another one here. Let's go for a deck of cards, okay? Actually, yeah, I better warm up on one before we hit the deck of cards. Okay. All right, these get a little bit harder, okay? We'll talk about money first, and we'll talk about the deck of cards. Okay, Mark has 2 quarters. And he needs 50 cents more to pay for the turnpike toll, which, by the way, that's interesting. You know how your parents used to, especially if you travel north, there are toll booths. Nowadays, you drive through the toll booth and they send you a bill. There is no one in the toll booths anymore. It was the strangest thing when we went up there. And then literally you have you can text a number and put your credit card number in, and you don't even slow down. There's nothing there. They do. It is an amazing thing, and so you text this number, and they're going, okay, what's your credit card? We'll take it off of your credit card, and you tell them the dates that you were going through that area and your license number, and it's an amazing thing. So this is a problem of the past. Okay, he needs 50 more cents to pay the toll. There are 4 dimes. And 8 quarters, and 9 nickels, and his little drink container. You know how that happens. You just throw the change in there already. If he reaches in and selects 2 coins at random without replacing the first one, what is the probability that he will draw a quarter and then a nickel? Okay, what's the probability that he will draw a quarter and then a nickel?